let's look at the different classification of numbers, and our goal is that we will be able to classify rational and irrational numbers. So let's start with the rational. So we notice all these circles are inside each other. That is because these are all types of rational numbers. So natural, whole, integers, those are all just more specific types of rational numbers. But then out here on the side we've got this cherry up here, and that is the irrational numbers. It's still a type of real number, but it's separate from rational. So all these things together make up rational, and then irrational is kind of out here on its own. So let's actually start with some examples of irrational numbers, and then we'll work our way through. So one example of an irrational number is pi. And if you remember pi, that's 3.1415. It just keeps on going. It does not ever stop, but there's also no pattern to it. So that is what really makes it irrational, is that it's non-repeating. Nothing ever repeats. We don't know what's going to come next. And it also does not stop. So that's called non-terminating, because terminating means it stops. So those two things are what makes a number irrational. It never stops, and it never repeats. Another example would be a non-perfect square, like 2 or the square root of 8. If you were to put either one of those in the calculator, square root of 2, square root of 8, you are going to get a value that just keeps on going. There's no pattern to it, so it does not repeat, and it does not stop, doesn't terminate. Let's jump to rational then. Unlike square root of 2 and square root of 8, the square root of 4 or the square root of 25, these are rational because if we put these in the calculator, these are exact whole numbers. Square root of 4 is 2. Square root of 25 is exactly 5. So they terminate, they stop. So if it terminates, it is rational, like the decimal 3.5. That's it. It stops after the 5. There's no more. It's done. Or negative 1.76519. Doesn't matter how long it is. If it stops eventually, it's rational. Same with repeating. I can have, let's say I have 2.6666. It can keep going, but if it repeats, it's rational. And it might not just be one number. Maybe it's got 3 numbers that repeat, like 7.125125 and so on. That's also rational because it repeats. So if it terminates or if it repeats, it's rational. That's the main difference. So let's start with natural next. Natural is when you were little and you first learned how to count. We started counting with 1, 2, 3, 4, and so on. As you got a little older, you learned that zeros in there, and then you started saying 0, 1, 2, and so on. So whole numbers are 0, but whole numbers are also all the natural numbers. So whole numbers are 0, and then 1, 2, 3, 4. And then integers are all those things, but it also adds the negatives, like negative 1, negative 2, negative 3, and so on. These are integers. So integers are negative 1, negative 2, negative 3, but integers are also 0, and they're also 1, 2, 3, 4, and all the natural numbers. So the kinds of builds on each other, and we get more and more specific. The trickiest part about classifying a number, is it rational or irrational, is that we might need to simplify it. For example, if you give me the square root of 16, well, I can answer that, and that's 4. If we think about just the square root of 16, that's rational. But where would I place a 4? I would place a 4 as a natural, or a whole, or an integer also. And then this is an example that we are going to see when, or we already saw when we looked at the squares and square roots. We had the square root of 25 over 9. And we learned that we can separate that into two separate square roots. So really that's just 5/3. And if I were to put that in a calculator, I would see that it's going to repeat. And let's add that up here also. So we didn't do that with irrational. Fractions are here too, so that 5/3 is actually rational. Even though it looks like it's going to be irrational, the square root of 25 over 9 is actually rational when I really look down to what does that value really equal. So fractions, if I can write it as a regular fraction, proper or improper fraction, if it can be written as a fraction with no square roots left in it, then it's going to be rational. So like 5/3, 1 2/5, -2/3. These are all rational. If I were to have a fraction that still had a square root, like square root of 3 over 2, the 2 part's rational, but because of the square root of 3, and I can't do anything with the square root of 3, I can't simplify it anymore, it's going to make that whole thing irrational. So if any one part is irrational, then it makes the whole thing irrational, as long as it can't be simplified, like we did in these examples here. If they can simplify, then it can be rational. If it cannot simplify, it's going to be irrational. And then we should also be able to name these also. So if, for example, you were asked, give an example of a integer, say -3. If you were to be asked, give an example of a rational number, I could say -2.5. If I were asked to give an example of an irrational number, instead of just pi, I can say 3 pi, because again, the 3 is rational, but because pi is irrational, if any part of this is irrational, it makes the whole thing irrational.